This way we can give them to the animators that actually sit down and create the action for the various shots we have. Then some other guys, while we do that, prepare simulations for things that are physically based, like somebody has braids, for example, on these things you want them to swing in the wind or do things like that. Somebody drops something off their pocket, you want gravity to act on this little thing. And then we assemble the whole thing in this layout process that brings all these objects together. Up to this point, there's one person working on one character, a different person working on a different character in isolation, then somebody working on the background. They assemble it all together in the layout, and they take care of shading it, which is the process by which we assign colors to all the things that go on screen, because we're making great stuff all the time. It's not cool. So once we've done that, there are a bunch of effects that also happen. Effects means, when you have smoke, dust, little pebbles, you name it, all these little things that come in very great quantity. These are all special departments that do stuff. And then, that's right, that's me, that's what I do. I'm inside that box. So we assemble the layout of all these things, and then we need to make pictures of them. We do, as you know, 24 pictures per second, so we need to be able to render very fast. And then, once we render these pictures, if my pointer worked, this thing would be much easier. Well, we composite them, and which is a process that was very necessary in the beginning. The night is composited on top of the church, so they had one guy with a camera shoot the actor in the church, different guy with the computer shot the night. Then you need to put them together, you compose them. If you take King Kong, which is some 20 years later, you have jungles which we go out and shot one day. Then you have the backgrounds, the sea, mountains in the sea, islands, whatever, which we paint in Photoshop, say. And then we have various pictures of actors moving, and the monkey himself, of course, and the digital part of the jungle. And then we need to assemble it all together, and that's what we do for compositing. And then you print it on film, and then you can take it to the cinemas to show it to you. So one of the techniques we use a lot, it's called ray tracing. Most of you will know. How many of you know what that is? Great. Okay. So you know all about that. So my problem in that picture is the scene, the big ball. My problem is that we have a lot of those big balls, and they have to be in memory somewhere so that some program can think about it and make the picture. So, well, says you, what's the problem? You use virtual memory. You want an address space that is maybe 200 megabytes. You only have 32. Okay, numbers are a little out of whack here, but you know what I mean. So you put some of this in RAM, some of this in RAM, some of this in the hard drive. Say that you work for a really big facility, I do, and you can have a really big hard drive because it's connected through a network. What you do is you take your local hard drive, you paginate it, same thing as you did with your address space. You also paginate your swap space, and then you send that away across the network. And your point is that essentially, anytime one of your purple lines wants to become blue, you want that to happen not more often than every 5 minutes. And that's the old way of doing it. But still, you want the changing your storage type to be as rare as possible as an event, because anytime you go to a different medium, it becomes typically 100 to 1,000 times slower. And so you can't take the far away ones very often, because those will kill your performance. So how do you do that? Well, let's see how much do we need to do first. So we want to trace 10 billion polygons. This has never been done before. So that's the contemporary design of the ray tracer for the studio, which is under development today. Standard ray tracers that you go and buy off the shelf now do 10 millions to 100 millions when you're live. So we're 2 to 3 orders of magnitude higher than that. So say that you have a tiny scene, the one you would use in OpenGL or something that's very simple. You would need an average of 16 bytes per point, which means that you need 160 gigabytes of addressable space. We need 100 bytes when we're shy, plus acceleration structure. So we're talking about allocating 1 terabyte. And that needs to be online. That's the space you use to do your queries on. This is not the remote location. And we don't have a terabyte of RAM. You can't even buy machines with a terabyte of RAM. Not in a single package. So there's also another point, which is how long does it take to do this computation? Well, you can say that, you know, normal ray tracer today, 300,000 rays per second per core, you know, not very optimized, but that can work. So main conflict. People that write papers can afford to write very optimized software that runs to the blood of the metal so that they can show the numbers. We don't do that. We have to produce pretty pictures. We can't compromise the quality of the picture because we want to run fast. So our software is by definition not optimized for speed because it has to be optimized for beauty. And so we can't use, you know, 3 million rays per second ray tracers per core as they advertise, because those don't do primitive variables. They don't do, you know, vertex geometry. They don't do displacement. They don't do a number of things that are foundational for the kind of pictures we're interested in. So how long would that take? Say we can do, we were saying, 300,000 rays per second. We have 10 billion polygons. That takes 9 hours at 1 ray per point. We need to do 256, so we're talking about 3 months. Can't do that. So we went out and talked to NVIDIA. And they told us that they could give us some guy who made a video, blah, 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 blah. So we worked on it a lot, and the prototype we have in our hands now does the same computation in 2 days, which is better. But, so, what do we need to do that? Well, first, we need infinite address space. We want to be able to allocate 1 terabyte as if it was the 16 megabytes of today. Well, 16 gigs, say. We want symbolic access to data, which means we don't care where data is. That's a problem for some.